Hello. I thought I would make a new video to replace a couple of old videos I have on how to make water waves. Um, so this is based on the NVIDIA Effective Water Simulation page, which I reference here. I'll make this slide deck. I'll put it in the details so anybody can get to it if they want. But if you have been here to this web page, they have a lot of functions and variables on how to create your own waves. And a lot of it is a little hard to understand and read. Some of the way the functions are written out is confusing, which can make this hard to use. So it took me some time to get through all of it and to get what I want out of it. So I wanted to make a video to show how to do it. So to start with, we're going to need a mesh, and we're also going to need a project in Unreal Engine. I just started a new one that's empty from the third-person map in Unreal Engine 5. So just wanted to say that. So if we go into Blender, we're going to need a plane that we know the size of, and we're going to need to tessellate it so that we can see vertices moving when we make waves. So let's do that in Blender real quick. So Shift-A, add a plane. Let's take a look at the size of it. Let's set it to 128 by 128 centimeters and apply all transforms. Go into edit mode here, and we'll hit Control E and we'll subdivide. So what I'm trying to do here, I want to tessellate it down to 1 centimeter edges. It's down to 2, it's down to 1. Just to make it easy, right? So we know that this thing is 128 across, and we know that each face is 1 centimeter. So let's go ahead and export that. I have a preset for static meshes, just exports the selected object, and on the geo it sets the smoothing to face. This way we don't get any warnings when we import it. So we'll start with that. There it is, tessellated plane. And I'm going to turn off generate missing collision, and I'm going to turn off generate light map UVs. I kind of like to do that stuff myself. So now that we have our plane, and if we look at it in wireframe, we'll see that it's very tessellated. And this is, so that we can see what our shaders are doing, right? Okay, so we have our tessellated plane. Let's make a new material. And let's set it to unlit, which makes it easiest to visualize first. Okay, so let's look back at our water simulation here. All right, so the first thing that we should do is just visualize something simple with a sine wave, an amplitude, and a wavelength, right? So let's go back to here. I'm going to put that on the other screen. So let's just go ahead and make, if you hold down 1 and left click, you'll get a constant. So let's do 10 times, let's select our tessellated plane and use that here. All right, so 10 times the sine if you type position here, you'll get world position, which is a bit weird, I know. 10 times the sine of 2, actually wait, let's do 2 divided by. Yeah, so we want the wavelength. So what I'm heading towards demonstrating here is that we want to be sure that when we choose a wavelength that it's accurately represented through the sine, that the size of it is real, right? That this wavelength is 128 centimeters. Okay. All right. So 2 divided by wavelength times x. Oh, we're going to need x, just x here. So let's set that to just R channel, which is x. Yep. That goes into the sine. And now we can go into emissive color. Okay. So this is 10 times the sine of 2x over 128, right? So if you notice here, the period of the sine wave is wrong, right? There's on and offs, there's multiple here. When our wavelength is 128, it should fit the whole plane because the whole plane is 128 across, right? And the thing to realize here is that the sine wave's period by default is 1, which is weird. Like, think about that for a minute. Normally, sine waves, you would want to pass in radians, which would mean 2 pi would create the whole period, right? So let's put in 2 pi here. So 2 times 3.1415 is close enough. So that's 2 pi. And now you can see this is starting to look a little better. But radio frequency, which is 2 pi f, or 2 pi over length, is the real way people do it. Is the real way electrical engineers use radio frequency. I don't know why NVIDIA has 2 over L without using pi. So now this will fix everything, right? There we go. So 2 pi over wavelength times x into our sine times this amplitude will give us this, right? So let's make a float 3 so that we can see the world position offset working as well. There. Our preview scene is cutting off everything, so let's turn off the floor. There we go. Okay, so you can see that that sine wave is producing this world position offset, and that 128 wavelength is filling up the whole plane, which is correct. If we do 64 here, we should see 2, right? Yeah, see? So our sizing is correct now that our sine has a period of 2 pi. Okay, I wanted to show that you could do all of this with a custom node too, for those of you who are interested in that. So custom node is a way to enter just HLSL code and do the exact same thing that these nodes are doing. Although these nodes allow optimization, Epic has a way of code folding that like reduces the instructions if you don't use a custom node. So you shouldn't always use a custom node unless there's some real reason, or you just prefer it. But I would be aware of possible performance issues. So we'll call this. So if we can just return a float 3, and we want nothing in x, nothing in y, and then we want what? 10 times the sine of 2 times pi times position. Right? Is that going to work? No, because our input, we don't have an input for pi. Although I guess I can say float pi equals 3.1415, right? Now the only thing we're missing is position. So we're going to need an input. Going to need an input for position, right? Should be this. Okay, I messed something up. Oh, forgot to do a close brace there. All right. So now we have done that, the exact same thing, within reason here. We didn't use the input for wavelength, and our output for the world position offset, is only the z, so the emissive color is blue instead of white. But you can see you can do the exact same thing here with that kind of code. All right. So we've done that. Oh, I wanted to mention something, which is the Nyquist frequency. So if you think about this wave and how, or this plane and how it's been tessellated, right? There is a limit at what wavelength can be represented on these vertices, right? So let me hook this back up so that we can see this better. I'll just kill this for now. And so what would that be, right? If you remember, we cut it down to 1 centimeter. So can it represent a 1 centimeter wavelength? The answer would be no, right? This scientist named Nyquist figured out that it had to be a little more than 2 times. So you'll see 2 is not right, but 3 we can start representing. See? So maybe even 2.1. Let's see what 2.1. Yeah, it looks pretty aliased. It looks pretty messed up, right? This is because the wavelength is just too small, or the frequency is too high to be represented by that, right? So be careful when you start to do this to realize that, because at really low frequencies, like or wavelengths, we could get really bizarre results. See, look at that. And of course, if you try to go, like 128 can fit on this, right? But if you do 256, you're going to get half of a wavelength. So you start not being able to see, right? That's only a very small part of it now. You can't actually see the waves. So keep that in mind, that the way you tessellated it and the size of your plane is going to affect what waves can be represented on it. And I talk about that here. Okay, let's move on to the general sine equation that's on the NVIDIA site. So you can see here this equation is amplitude times the sine of the dot product of the direction and the position in XY space times this WI radial frequency plus time times this QI, which is a phase constant. And I wrote them out here a little more clearly. Amplitude times sine of the direction. And of course wavelength is 1 over frequency. Radial frequency is 2 pi f, or 2 pi over L. The phase constant is speed times the radial frequency. And I wrote down some of the units there. So let's go ahead and build that material. Let's just call it. Right. Let's set it to unlit again. So the first thing we're going to need is the direction. So I'm going to use a parameter for this. But this direction is only in X and Y. So you're going to want to append an XY vector like that to make 1, right? So we've got the direction. Yeah, you might want to follow along with the equations on the side on another screen or something, because I don't have an easy way of showing it at the same time. But direction dot with position in XY space, if you remember. So I always like to exclude the offsets unless there's a reason I want them. Okay, XY position. See, let's make the direction be just in the X direction right now. So now we're going to multiply that by the phase constant, right? So the phase constant is 2 pi over wavelength. So hold one, click, 2 pi if you hold down S and left click, you will get a parameter that's scalar. So let's go ahead and keep that at 128 so we can make sure that it's the right size. Okay, so this is now our radial frequency, so I'm going to mark it, right? This is our direction. This is our position, right? Okay, so if we multiply the dot product of that times the radial frequency. We're going to add, next we're going to add time. So we go add time times the phase constant. So the phase constant is speed. I'll just leave it at 0 right now. Speed times the radial frequency. So that's our phase constant, which I will just call Q for now. Even though it's a Greek symbol, they're not easy to do in here, or it may be even possible. I've not tried. I wouldn't like put Unicode characters in here. That would possibly cause issues. Okay. So that is all the stuff that we're going to feed into the sine. If you remember, once again, the sine wave needs 2 pi as its period if you don't want things to be messed up. Let's multiply this by a amplitude. Let's take a look at what it looks like. There we go. That's exactly what we expect. 1 full period of the sine wave in the x direction. And if we want the world offset to be in the z direction only, which we do, we can do this. So the amplitude's pretty small. Let's do 10. You can see that is working, right? Yep. All right, so this is looking good. You can also do this in a custom node, which I have in the slides if you want to see it, but I'm not going to do it right now. So what if we make this lit? Okay, let's unhook this. Let's make a base color that's just gray. So 0.18. Let's make a, no. Let's make it metallic. We're going to make it really reflective just so we can see stuff. Right? All right. So if we look at this now, you can see the waves are bending it. And we're seeing a shadow. But the normals are totally not updating, right? So we need to also calculate the normals. So let's do that next. So one thing you can do, if you don't know how to calculate your normals and you just want to see what the normals might look like or should look like, you can do this cool trick. So take position, and this is after the offsets, right? So this is the actual position of each vertice, and we're going to use ddx, ddy, which are the change in x and the change in y. I'm going to feed those with the position. And then we're going to do a cross product between the two, and that creates a normal. So let's visualize that in both ways. All right. So you can see our normals are now bending like they should. But they're usually very harsh. You can see like these lines in here. It doesn't smooth the normals. It just creates exact normals. So this helps us to know what this should look like. You know, it's a ground truth we can compare with if we need to. So let's just leave that there, but we want to calculate our normals directly. All right, so let's talk about that, how to do that. So the NVIDIA site has equations for it. It says the normal is the cross product of the binormal and the tangent vectors, right? Oh, one thing I forgot. When you do this kind of thing for normals, you got to turn off, under advanced here, you have to turn off, wherever the heck it is, I'm too far down, I'm trying to turn off tangent space normals. Hey, there they are. See them? All right, tangent space normals. Yes. Because these normals we're generating are in world space, right? They're not in tangent space. So be sure to turn those off if you want these to look correct. Anyway, to continue again, on the normal equations here, normal is the cross product of the binormal and the tangent vectors, which is kind of what you do here. That's what this is. But we can calculate it directly. The normal is minus the partial with respect to x of this equation h, minus the partial with respect to y of this equation, of the same equation, and 1. So if we look at how to partially differentiate this equation, you can see here it's just the differential of that original sine equation, which, you know, differential of sine is cosine, right? And then you differentiate the stuff that's inside, and that all pops out. So how did that happen? If you want to understand how you get this value and what this means, I did a little example here. So here's the original equation, and we're doing a partial with respect to x, right? So we know that the differential of sine is cosine. So we just do ai times cosine, and we got the original thing that's in there, times the partial of what was inside of it, right? So then we need to rewrite what's inside of it to make it make sense. Let's replace the di dot xy part with the definition of a dot product. So this is for each each component in the vector, right? So 1 would be x, 2 would be y. So I replaced it with the definition. So we have the direction in x times x, the direction in y times y. That's what these are, right? The di dot position. And if you think about it, so since x is the only variable here, this gets wiped out. This wi multiplies by this, then this x being differentiated returns the direction in x times wi. This part goes away as well, right? So that's how you get there. Okay, so let's build that result. If you notice, the thing being fed into the cosine is the same as what was fed into the sine, right? Here's what's in the sine, here's what's in the cosine, so we can start with that. So let's go ahead and just pop a cosine on here. Remember, 2 times pi, or you're going to get the wrong period. So we take the same thing that's feeding the sine, we feed the cosine. Now we multiply by the amplitude. We multiply by the radial frequency. We multiply by -1. I'm going to combine some calculations here to make this cheaper. All right, and now this result here, we need to do the things that make it specific for x or y. So let's go ahead and make a float 3. So if you look back on this page, you'll see it's 1 in z and the minus of these two, right? So let's pop 1 in z. Okay, and this multiply is going to be with the x component of the direction. So here's our direction, right? So we need to use a component mask, which is Shift-C to pop that up, and let's go ahead and do x. So we multiply by x, and this will create our x normal. And now we can duplicate this, use the y mask instead. This goes here again. Whoops. -1. Oh wait, no, not -1. Doesn't matter. There's the x mask, there's the y mask. We've already got the -1 there. I forgot to hook up that to the direction vector there. Okay. we go. You can see the normal. Let's compare it to this one here. It looks right to me? Question mark. Let's see. Let me re-look through the equation here. So cosine times amplitude times radial frequency times -1 times the x component of direction. Yep. All looks good. So let's deconnect the emissive color here and look at those normals. Does that looks about right to me? So now that we've done that, let's see, we should convert this to a material function if we want to make some Gerstner waves, because they're very similar to this, and usually the point of Gerstner waves is to add multiple waves together, right? So let's make a material function. So really you can just copy all of that, paste it into here. And that output there was the world position offset, and this output here was the normal. We need another output function output. Right. Okay. So we need to get rid of all of these scalar parameters and vector parameters and make them function inputs. So look, you can hold control and left click. You can move it like that. So there's amplitude. Let's see. Probably easiest to hit Control D and just duplicate some of these singular scalar ones. Let's name this one speed. So speed, default to 0. Amplitude, let's default it to 10. Okay, let's create a wavelength one. I'll default that to 128 since it fits our plane. Alright, really the only thing left I think is direction. And it is actually a vector 2 because it's an XY direction. Oh, one thing I forgot here. We've got to normalize this in case somebody puts in something nasty. So we don't need to append it anymore. So we need to normalize this. Otherwise you will get weird scale results. Like if you make direction 2 instead of 1 on the X, it will scale things by 2. Okay. So this is still direction, right? D. Oh, look, we lost where the direction was coming out there. So let's fix that. Actually, I should call it direction after the normalization instead of here. Yeah, to make sure that that's where I use it from. Okay, now that we've done that, let's put that material function back in here. And move the normal. Right. Here's our amplitude, which we can just hook directly up here. Here's our speed. Here's our wavelength. Here's our direction. All right, there we go. So our normals are good, and we've got a singular material function that does all of this. Okay. So that all looks good. The next thing we need to do is turn these into Gerstner waves. So the Gerstner wave Z part is the same as what we've already done, but adds an X and a Y part. And the normals also change. So let's go ahead and build that new material function if we want Gerstner waves. So if you duplicate this one, let's get rid of this. Okay, so this Z part is already fine, right? But we need to add some more cosines for the X and Y part. And I just copied it so that I would keep the period correct. So the cosine is actually fed with the same thing the sine is fed with as usual. It's multiplied by QI AI. So what is like an uppercase QI? The uppercase QI is the wave constant. So let me do that real quick. So well, first we're just going to multiply by amplitude because that's the AI part. All right, let's see. Whoop. So let's look up the QI part real quick. Here it is. So QI is 1 over WI AI number of waves. Okay, so 1 divided by radio frequency, WI, times amplitude times the number of waves. Oh, whoops. That needs to be a function input, right? A scalar. Okay. So this is the uppercase QI. Okay. So it's the cosine being fed with that stuff times AI times QI times the direction X for the x one. So let's mask that for the x. Let's get the direction as usual. So that's the x part of the direction. So that could be we're going to multiply that by the cosine. Yep. And that there will be the x part. So let's pop that into x. Oh, I forgot. Good Lord. This 1 is actually the steepness. Let's set that to a scalar, and I'll put it to something small. There. Okay. Okay, so that's giving us the x part, and we can get the y part by doing this again, but with y, right? Yeah. All right, let's go back to our, oh wait. So here's our sine wave. Let's duplicate this. And we'll put the Gerstner wave function in there instead. Okay, let's see. All right, so we've still got the world position offset working. The normals are now going to be broken because the normals have to change a bit. Okay, so that's the world position offset. And it's really hard to have this not become a mess, given like all the things that are intertwined. The real way to make this not a mess is to do it in the custom node. But anyway, so let's look at our normals again. So if you look at the equation for them, here's the x normal, the y normal, and the z normal. And we'll have to do a head calculation here. So let's just kill this. So the normal for x is going to be WA. So that's the radio frequency times the amplitude. So we'll multiply that times the amplitude. That is going to be called WA. Okay. The cosine fed with the normal stuff, which we have actually up here already, is going to be called C. And the sine fed with the normal stuff is going to be called S. Like that. So now we can go ahead and directly construct these guys. So the x and the y are all negative, so let's go ahead and just multiply by a -1 for them. Then we're going to multiply by, oh yeah, so we got WA times -1 times cosine the C, which is up here. Yeah, so this is, oh my god, do the comment. Alright, this is WA. The only thing we're missing is the things that converted into the X and Y from the directional thing again. So actually, we have d dot x here, right? Let's move that back here. We've got d dot y here. So we can go ahead and multiply this by d dot x. And that is our normal in the x. Now if we multiply this by our d dot y, we'll get the y version. Okay, so now the z one is a little different because it's a 1 minus the sum of all of them. So we'll construct it slightly differently. So it's WA times S instead, wherever S is. There's S. That's WAS times QI. The uppercase one. There we go. So now if we go back here, the normal actually is wrong a bit. Because it needs to be 1 minus on the z. And you'll see the reason why I'm doing it this way in a bit, because if we want to combine multiple waves, this is the only way to do it, right? So this normal is going to be the x, the y, and then 1 minus this. There we go. Oh. That might help. There we go. Okay. So we now have normals. We've got one wave. We've got world position offset. Let's create a material instance. And let's put this plane in the world somewhere. There we go. So we put the Gerstner waves on it. Let's go ahead and save all. Okay, so let's take a look at our material instance. Just close all of these. So if we change the speed, it will move, which is good. Change the steepness. You can see the steepness in there. That needs to be kept pretty small. See the wavelength? We can make it 2, instead of 1. There's only one wave right now. We can change the amplitude, right? Make it smaller, make it larger. If you set the steepness to 0, it will zero out the x and y movement, or it should anyway. And you can also change the direction of the wave. And since this is normalized, like we can set this to 1, 1, even though that's not a length of 1 vector, and it will, be at an angle like that. Yep. So you can see that's working. Why don't we go ahead and make it look a little better? So if we go into the Gerstner wave material, we can change the shading model to single layer water, right? So you have to add a single layer water material input, and we're going to need some absorption coefficients. And I just kind of like to divide this down by 100 or something, because it's a very small numbers that start working. Also, we've got some other controls now, so let's go ahead and just make a base color. Let's make this. Right, we just want to have controls for all of these things now. Okay, let's set some ranges for those guys. There we go. Actually, let's set this to something. Let's set this to something too. Okay. So now you can see we have water that's clear. So if we go back to our Gerstner waves here, you can adjust the opacity. And if you turn this up, you'll see more of the base color. That's what that does. So at 0, you don't see any base color. And if you change the absorption coefficients, you get more absorption as the light passes through. But you got to remember, absorption is kind of like the opposite, right? Like it's absorbing the opposite of this color. So if you see I'm on this side, you're going to see blue, right? Like if I go over to red, you're going to see that lighter blue. Purple, you're going to see green. So go to the opposite side of the color wheel of what color you want to see, right? And refraction is important. So I know like real water or glass, real water is like 1.33, but sometimes the refraction looks very crazy strong. Don't be afraid to do something like 1.03 so that you can see the waviness, but it doesn't overpower, Okay. So that's one Gerstner wave. Let's make it so that you can have more than one, right? So what we need to do here is make multiple of these Gerstner wave functions, right? And then combine them. Let's move this out. So let's say we're going to have up to 4 waves. So if I convert this to a parameter and I call this speeds, then the red one could go to this first one, right? I could duplicate this and call them wave lengths. Let's put like 128, 64, 32, 16, right? And we'll put the red one in there. Yeah. Let's see. Let's do steepnesses. Let's just set those all to 0.2. And then we're going to have amplitudes. And as you're doing this, you're probably thinking, what if I want an arbitrary number of waves? I mean, obviously this limits you to some number of waves to do it this way. I have not figured out how to do a whole lot of waves, like if you want 100 different waves, let's say, without doing something like FFT waves, which is just a total different subject. So we won't talk about that as of now. Maybe I'll learn that in the future. Okay, so here's direction 1 and 2, we'll say, right? So create another append, and direction 1 and 2 will go into there. So the second one, let's make it just like that. Now if we duplicate this guy, we're going to get direction 1, 2, 3, 4, right? We can make that one -1, minus, I'm just arbitrarily kind of choosing whoops. I'm trying to duplicate this. I keep hitting Control W because that's what you used to do in the old version of Unreal Engine. And it is confusing me now. Alright, so there we go. So we should be set now to have up to 4 waves. So let's duplicate that guy. And this one is going to be the green channel. Right? So green speed, green wavelength. It's going to be the second. Whoa, didn't mean to do that. Second direction. Number of waves is always going to be the same. Let's go ahead and set that to 4. Put that out of here. Steepness is going to be the green steepness, going to be the green amplitude. So there's 2 waves. Here's our third one. It's going to be blue, blue speed, blue wavelength, blue steepnesses, blue amplitudes for this direction. And then our final one, which will be the alpha. So alpha speeds, alpha wavelengths, alpha steepness, alpha amplitude, final direction. All right. So now we have 4 Gerstner waves that we can add together. So how do we combine them, right? Well, the world position offsets can just add. If we, let's see. Let's go back to the Gerstner part. Yeah, there you go. Look, they're just added together. This X, we're going to ignore that because we're talking about a world position offset. So we don't want to add the X to it. So let's just add these all together. Go. Okay, so far as the normals go, they all add together in their own fashion here. So actually, the X and the Y's add, but the Z does 1 minus the add. So if we add them together, I failed. I added the 2 wrong ones together, didn't I? So those first 2 go into this one, go into the third one, go into the fourth one. Yeah. All right. So that's all the normals added together. Yeah, we break out the float 3 components because the x and y just are added together, and the z needs to be 1 minus. Wow. So let's go ahead and take a look at this, huh? That's pretty heinous looking. All right, so let's set the amplitude of all the waves except for the first one to 0, so we can just see 1. And let's set its speed so that we got something happening. Right? Okay. Now let's turn on, I'm going to reduce its amplitude. All right, let's turn on the second wave. Oh, it has no direction. It has to have a direction. Let's see. Okay, so you see that wave is kind of that way now. Let's make it pretty small maybe. And set some speed on it. No. If you do these even multiples, you will get not good looking things. So let's make this one 128. It's okay. Let's make this one like 75. So there's 2 waves. Here, that one's. Three waves, 4 waves. But anyway, so you can. Wow, look at that one. That one's pretty gross looking like that. It's because the wavelength is so short, right? But anyway, this is how you do it to combine a bunch of different Gerstner waves. And the actual values to get like good looking stuff is kind of an art. But that's one way to get 4 or some arbitrary number. I guess if you wanted to do 8, you could just like put what I did here into a material function and then duplicate it. Your base pass vertex shader would start getting crazy, I would think. This is pretty expensive material now, 916 instructions. Single layer water is not cheap. Yeah. Okay. What if you want to make waves that are dripping, like circular waves? So that's the final thing we're going to talk about. So circular waves, they use that same sine formula, but the direction vector is a little bit different. All right, so if we take that material function for sine wave, let's make a circular wave one. So the only difference here is that direction is changed. So let's see here. Direction is now the difference in position, x, y, and a center. So let's call this center. And we'll do a subtract of the world position and the center. Oh, it's the XY world position and the XY center only. And then we will normalize that. And that will create our new direction. So let's make a material so we can see this. do the unlit thing as usual, just to test it at first. And we're going to need our plane. There you go. So we have a circular wave now. You can see. So if this goes here, you can see we have a circular wave. It looks like a octopus or something, doesn't it? The normals will still work. The normals calculation, the only thing that changed was direction, so that will work. So let's go ahead and set this to default lit. Oh, wait. I got to make sure that our tangent space normal is off too. So default lit, put that into normal. I can visualize it a bit better. There we go. It's pretty cool looking. All right. So this would be good for like a rock falling in the water or something, or a drip of water falling in the water over and over, except it's going the wrong way and it doesn't ever mask. It's not like masked off. So let's go ahead and fix a couple of those small things. So the first thing we could do is reverse time. And the reason we want to do that is so that it looks like it's coming out from the center, right? That looks better. Then the other thing we could do is the amplitude here. We can multiply this by something to make it fall off, right, over a distance. So we want the distance from the center find distance. There it is. Okay. So we take the distance from the center to the XY world position. Right? Let's divide that distance by a scalar we will call fall off distance. Let's say 64. Okay. I'm going to saturate that, which clamps it between 0 and 1. Then, so if we preview this, let me get the plane again. There you go. Let's do a 1 minus. There you go. So you can see here is where it's going to be affected, right? Let's take a power. So we'll call this let's just set that to 1. There we go. So now if you adjust the fall off power, you know, it will cause it to fall off faster or slower. All right, so if we take that and we multiply that by the amplitude and take that result as the amplitude, now we're cooking with gas. Let's see, fall off distance. There we go. So you can see it's getting smaller as it gets away from the center. All right, we can adjust the fall off distance and power to make it so that it doesn't, the ripples don't reach the edge if that is something you want. The center has an interesting little dollop there. It's probably where it's trying to normalize 0, 0, 0. I have to figure out how to fix that sometime. But you can see this is how you would do that. And I believe that's it for now. So if you have any questions on how to make waves or how to look at this stuff, let me know. If you know better ways of doing any of this, definitely let me know. If you know how to make the water look better, let me know. I didn't do it in this tutorial, but you can put obviously texture normals that pan on the top and so on. I didn't want to do that yet, and I'm aware of that, but there's a lot of cool tricks you could do with that and refraction, distance fields to show ripples. There's all kinds of cool stuff you can do. But I'm going to stop here for now because the main thing I wanted to show was the math. I hope you enjoyed. Thanks.